Alright, you guys, 4.5, the real zeros of a polynomial function. Alright, I'm going to write out these two things right here. Alright, the division algorithm for polynomials. If f of x and g of x denote polynomial functions, and if g of x is a polynomial whose degree is greater than 0, then there is a unique polynomial function q of x and r of x such that if you divide the functions, you're going to get some quotient plus the remainder over the denominator. Or you could write it like this, where r of x is either the 0 polynomial or a polynomial of a degree less than that of g of x. I'm hoping you guys are all familiar with long division. I'm hoping you guys learned that in Algebra 2. We will do some examples in class, and we're going to do some examples in the notes here. This one might be new, the remainder theorem. If f, it should be, yeah, that's what it says. I'm going to change it up. There we go, a polynomial function. If f of x is divided by x minus c, then the remainder is f of c. Alright, let's try that. Find the remainder if f of x equals, this function is divided by x minus 3 or x plus 2. Okay, so we could use long division or synthetic division, but it's actually easier to use the remainder theorem that we just learned. Okay, we have x minus 3, so f of 3 is 3 cubed minus 4 times 3 squared minus 5. So I've got 27 minus 4 times 9, which is 36 minus 5. And I'm confident you guys can all do that. This equals negative 14. So rather than doing long division or synthetic division and getting the remainder, this is the remainder. That's all we have to do. X plus 2, we're going to have f of negative 2. So we do the same thing again, negative 2 cubed minus 4 times negative 2 squared minus 5. And if you do all that out, you're going to end up with negative 29. Alright, let's take a look at the factor theorem. Okay, I'll write out the theorem. Alright, if f of c equals 0, then x minus c is a factor of f of x. If x minus c is a factor of f of x, then f of c equals 0. So basically, this is something you guys kind of already know. If you have, for example, I don't know, x squared plus 3x plus 2 equals, we'll call this f of x for now. If this is your function, okay, and you want to know what the factors are, you would just set it equal to 0, right? And if you factor this, you'd get x plus 2, x plus 1. And these would be the factors, okay? Because that's what you get when you set equals 0, okay? Also, if you were to solve this out, you get x equals negative 2, x equals negative 1, and you were to plug this in to your equation, you would get 0. Okay, so that's basically what this is saying. They're just using variables instead of numbers. Alright, but now we're actually going to set out and prove this. As soon as I erase all this over here. You can keep it in your notes if you want. Alright, before, when we were talking about the division algorithm, we ended up with a function that looked like this. Okay, so, let's see here. Suppose that f of c equals 0. Okay? We know from what we learned before that f of x equals q of x times g of x plus r of x. And this is in the box right above this in your notes. I'll show you real quick. Right over here. Okay? Now we know from the remainder theorem, if g of x is x minus c, then r of x is f of c, because that's the remainder, right? So let's plug this in. F of x equals, and we write the I'm going to write the g of x out in front. So I've got x minus c times q of x plus f of c. Okay? But we have already determined that f of c equals 0. So f of x equals x minus c times q of x. And this just goes away because it's 0. Actually, I'll write that in there. Okay. Alright, so if this is true, then x minus c has to be a factor of f of x. This triangle here means therefore. Okay, so we have just proven the first statement. Let's take a look at the second statement. I'll just draw a line here. I'll draw a straight line. Here, kind of sort of straight. Okay, so suppose x minus c is a factor of f of x, because now we're proving it the other way. Okay, so x minus c is a factor of f of x. So there is a polynomial function such that f of x equals x minus c times q of x. That's the only way it could be a factor, right? So by replacing x with c, we get this. Okay, obviously c minus c is just 0. 0 times anything is 0. Therefore, f of c equals 0, which is what this says. Okay, so we've proven it both ways. Alright, let's do an example. Use the factor theorem to determine whether the function has a factor. And these are our options. The factor theorem states that if f of c equals 0, then it's a factor. So let's just plug in whatever we have. F of 1, we plug in 1 into all the x's. I'm confident you guys can all do this, so I'll just tell you it does in fact equal 0. So this one is a factor. Now let's plug in the other one. F of negative 2, you get 2 times negative 3 cubed minus negative 3 squared plus 2 times, oops, I'm putting in negative 3 instead of negative 2, my bad. There's this. There we go. 2 times negative 2 minus 3, okay? And I'm confident you guys can all do that, so I'll just tell you. So we get 13. So this is not a factor. Alright, I will let you guys try this one. Alright, number of real zeros and Descartes' rule of signs. Alright, a number of real zeros. A polynomial function of degree n, and it's greater than or equal to 1, has at most n real zeros. So for example, if you have x to the 4th power plus x cubed plus w, whatever, the highest number of real zeros it can have is 4. Okay, so whatever the degree of the polynomial function you're dealing with, that is the most real zeros it can possibly have. It might have less, but that's the most it can have. And before I go on to Descartes' rule of signs, as I was writing this down, I was just realizing that I'm an idiot. So feel free to laugh at me. If you look up here, let f be is actually correct. Let f is does not make any sense. I don't know what I was thinking. There's a way to go back and change it, but I don't want to, so feel free to just laugh at me. I'm going to leave it in the video. Alright, Descartes' rule of signs. Let f denote a polynomial function written in standard form, okay? The number of positive real zeros of f either equals the number of variations in the sign of the non-zero coefficients of f of x, or else equals that number less an even integer, okay? The number of negative real zeros of f either equals the number of variations in the sign of the non-zero coefficients of f of negative x, or equals the number less than an integer. Okay, what on earth does that mean? I'm just going to do an example, and then hopefully it'll make sense. All right. Discuss the real zeros of f of x equals blah, 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 blah. Because the polynomial is of degree 6, by the number of real zeros theorem, there are at most 6 real zeros. Since there are 3 variations in the signs, okay, so when I say variations of the sign, this is positive, this is negative. This is negative, this is positive. Positive to positive, positive to negative. So it goes from positive to negative, that's 1 variation. It goes from negative to positive, that's 2. Positive to positive, no change. Positive to negative, that's 3. And then negative to negative, that's it. So there's 1, 2, 3 variations in the sign of the non-zero coefficients of f of x. So, by the Scart's rule of signs, we expect either 3 or less an even integer. So, subtract 2. So we're going to expect either 3 real zeros or 1 real zero. I'll write that down. Either 3 or 1 real zero. Okay. So now let's take a look at f of negative x. If I plug in f of negative x, it's even here, so it just stays. It's even here, so it stays again. This one is odd. Okay, so the sign is going to change. This one's even, so it stays. This one's odd, so it changes. And then the 3 stays the same. Okay, so now we're going to do the same thing again. It goes from positive to negative, that's 1. Negative to negative, no change. Negative to positive, that's 2. Positive to positive, positive to negative, that's 3. There are 3 variations in sign, so we expect either 3 or 1 negative 0. So in this case, whether you use positive x or negative x, you have the same result. Okay. Yeah, and equivalently, we know that the graph, if we were to graph this, there's either going to be 3 or 1 x-intercepts. Okay. In this case, they're not asking you to solve for the real zeros, they just want you to discuss it, so this is all they're looking for you to do. Go ahead and do the same thing over here. Alright, example 4. List the potential rational zeros of the function. Okay. There's actually a theorem that I forgot to put in here. Let's see here. I'm just going to stick it underneath this one because there's some space. I'll put a different color. You can stick it anywhere in your notes or on a separate sheet of paper. Just make sure you have this theorem because it's kind of important. Okay, I'll write it out and then I'll talk about it. Alright, the rational zeros theorem. Let f of x equal some polynomial. Okay, in standard form. In which a of n does not equal 0 and a naught does not equal 0, where each coefficient is an integer. If p over q in lowest terms is a rational zero of f, then p must be a factor of a naught and q must be a factor of n naught, or a sub n. Okay, so p is going to be a factor of the last term and q is going to be a factor of the first coefficient. But you know what, I just realized that I forgot to write in. These are positive real zeros. And these are negative real zeros. So we know it can't have more than 6 total. 3 or 1 positive and 3 or 1 negative. And you know what? I think because of time, I'm going to put the next example on the next page.